There we go.
There we go. Okay, sorry. That'll work. Anyway, so we've never gotten close enough to take a proper picture of them yet because flying very close to particles running around Saturn at 30 kilometers a second is a bad idea. So we still have to rely on pictures of what it would be like to stand in the rings. We have pictures like this, where you have literally particles almost a single layer thick. So if you stood on one of these, you wouldn't see much above your head or below the particle you're standing on, but an infinite horizon. This is purely alien. Nothing else in the solar system looks like this. And it's natural to ask, why does this exist around Saturn? This is very unlike anything around us. In our area, we see the moon, round things. Planets have tons of moons. Why does Saturn have rings? Well, basically it's because this material in the rings cannot come together to form a moon because it's too close to the planet. If you think about the moon or other objects, they're held together in part by their own gravity. But if you're orbiting another object, that object has gravity too. And which one wins? We actually can say there's a realm of rings and a realm of moons around every planet. If you're far from the planet, the gravity of your own gravity can hold you together. But if you get too close to the planet, inside a critical distance, which is called the Roche limit, astronomers make up names for things, the gravity of the planet wins. And if you have a bunch of individual particles, they want to move independently, not all as a unit. So they get spread out to form a ring. Now, around this limit that defines the world of rings from the world of moons exists around every planet. On Earth, there's nothing in that zone except the stuff we put up there. But around the big planets, like Jupiter, Saturn, Uranus, and Neptune, there's material there. All four of these planets do have rings. And other objects have them as well. So rings in and of themselves are not rare. They exist in multiple places. But Saturn's rings are really special. All of the other rings are hard to see. They weren't seen until the 1970s. Saturn's rings could be seen from telescopes for hundreds of years. They are more massive, they are brighter, they're more extensive than any other ring system by far. And one of the questions that we have been trying to answer for the longest time is, where did those come from? And there's basically two answers that it could be. One is, it's part of how Saturn formed. When Saturn formed from a cloud of dust and gas in the early solar system 4.5 billion years ago, when Saturn formed and its moons formed, something about that process gave it rings. That would say that basically ring formation is part of making planets, and Saturn's formation was special in that regard. That's one option. The other option is that Saturn didn't form with rings, it got them later. Something got inside the Roche limit and broke up. Maybe a comet, maybe a moon, maybe something. In that case, it tells us something about the Saturn's history is unusual. This happened at Saturn, but not at other places. Now, these don't necessarily sound that different if you first think about it. Maybe that getting something close happened early on. But in practice, these two pictures and the people who advocate for them have moved further and further apart over time. There is now kind of two camps. It's really a bunch of scientists arguing with each other, so calling it camps is kind of not right. There's a group of people who say the rings are old. They're part of the solar system that formed 4.5 billion years ago. There are other people who now argue very strongly that the rings are around 100 million years old, which is not recent, but on geological time scales, fairly recent. There are dinosaurs less old than the rings in that case. Those are two very different ideas. And there's good things and bad things for both. This is a good old-fashioned scientific debate. We have the idea the rings are old, the idea the rings are young. You can't always prove something, but you can find problems with things and potentially rule them out. So people have argued that the rings can't be old and that the rings can't be young. This has been going on for decades now, and I want to explain the logic here. People say the rings can't be old based on what they're made of. They say they can't be young because of how they could have formed. And I want to try and explain that. What are the rings made out of? That I can answer. The rings are made out of water ice. That is the same sort of ice that freezes all around everything in this place. We know that from looking at how the rings reflect light. This is a plot just showing the amount of light the rings reflect as a function of wavelength. And all of the features, all the variations with wavelength are typical of regular old water ice. You look at wavelengths from ultraviolet to the radio, it's all water ice. Best measurements, it's 95 to 99% pure ice. That's one of the reasons they're bright. It's like freshly fallen snow. There's nothing else in it. Okay, there's 1%, maybe 2%, of something else. That is unusual. There are other things in the outer solar system, like comets, like other moons. They're not ice. They have ice. We've flown by comets like this one, which is called 67P, or two Russian names I'm not going to try and pronounce. This thing has a large fraction of ice, but it also has a fair amount of rock and carbon compounds. If you actually try and show this thing at its true brightness, you can't see it. It's as dark as charcoal. This is what most things in the outer solar system are made of. Saturn's rings are different. Now, it having a different composition isn't intrinsically a problem. It just formed differently. That's fine. The problem is these things are crashing into the rings all the time. We know that. The Cassini mission showed us that. These little blemishes on the rings, like that one and that one, that's a comet hitting the rings and breaking up and producing a cloud of debris. So these things that are not pure ice are getting mixed in with the stuff that is. Do that for 4.5 billion years. Can you keep the rings 99% ice? The calculations seem to say no. That's a problem with the rings being old. Okay, that's a legitimate argument. What's the problem with the rings being young? Well, the problem with that is if you want to make the rings recently, you need to get something close to Saturn. Something needs to get in and break up. Something needs to move close to Saturn. That's hard to do nowadays. The orbits of most planets, most objects, they don't change that much. There's very few, giant impact sort of events. If we think about things where two objects have gotten really close and crashed into each other, we have to go back to the early part of the solar system. Clearest example of that is our own moon. Our own moon is covered by craters that were created when something very big crashed into it. All of those craters, thanks to Apollo data, are more than 4 billion years old. The early part of the solar system was a very dynamic, maybe violent time. That's when things were getting close to other things. Not now. And people go, what's the probability that something like this happens in the last 100 million years? They get small numbers. The most likely time to put something in orbit around Saturn is early. Now, that's, again, a legitimate argument. Maybe you buy it, maybe you don't. That's fine. But we have these two arguments. How do we decide between the two of them? Well, these arguments were first developed back in the 1980s, before the Cassini mission came. And the hope was Cassini would help settle this. Now you might wonder, how do you settle this with a spacecraft? Well, there was one number that both people who thought both of these ideas agreed would be important. And that number is the mass of the rings. How seriously do you take these two arguments? That depends on how much stuff is in the rings. Just to think about that a little bit. Let's say the rings have a lot of material in them, like they're very massive. Well, then it takes longer to change their composition. Maybe they can survive for 4.5 billion years and still be 99% pure if they're high mass. So if you make the high mass the old ring idea, the objection to old rings gets a little weaker. While if you try and make the rings young and really massive, you need to get a lot more material close to Saturn. That's harder. So as you make the mass higher, you start favoring the idea that the rings are old. On the other hand, if you make the ring mass low, it's easier to change their composition. They won't. It's harder to keep them 99% ice for 4.5 billion years. And maybe it's a little easier to imagine something getting close to Saturn. So if the mass is low, where high and low are to be determined yet, we start to favor a young ring. And everyone working on this agreed to this. That the higher the mass, the more likely they're old. The lower the mass, the more likely they're young. Everyone agreed with this, and so one of the things Cassini was to do was measure their mass. And it did it. And in fact, we did it multiple times to make sure we did it right. The one way we could do it is just look at structures in the rings. Those patterns of bright and dark bands, those are things that happen when you poke the rings in certain ways. If you poke the rings with gravitational perturbations from a moon, you can disturb ring material and have it propagate out. Just like a sound wave propagates through air, you can produce a wave in the rings. The properties of waves depend on what they travel through. The properties of these waves tell you the surface mass density, and they're all over the rings. We can add those up and measure the mass. That's one way to do it. Another way to do it is measure the gravity of the rings directly, which we did at the end of the mission. Cassini normally flew outside the rings because flying through the rings would be bad. At the end of the mission, though, we were able to fly between the planet and the rings. That meant the gravitational pull of the rings on the spacecraft flipped direction. And we could actually measure the gravity field of the rings directly, which was hard because we were still trying to measure it relative to Saturn, which has a lot more mass. And both of these gave the same number, fortunately. What's that number? For those of you who like numbers, it's 2 times 10 to the 19 kilograms. So 2 followed by 19 zeros. That is a number. It is a smaller number than most of Saturn's moons. These moons on this side, Mimas, Enceladus, Tethys, those are normal roundish moons. There are some smaller moons, but it actually works out in terms of these things. It's on the low side. it's favoring the idea the rings are young. Just to be, again, I want to be explicit about this. That mass says that every square meter of the ring, so every chunk of the ring is about this big, has a mass of about 500 kilograms, which is a fair amount. But we know how much cometary schmutz is going through that square meter. It turns out about 15 micrograms are going through that area every year. Take the ratio of those numbers, you can figure out how long it takes for about 1% of non-icy stuff to get into the rings, and it's of order a couple of 100 million years. This is consistent with the rings being young. This we expected. We didn't know what the answer would be, but we knew we would get a number and we'd have to deal with it. Cassini didn't just give us this number. It also surprised us and gave more ammunition to the people who said the rings were young. Remember, the spacecraft was flying between the planet and the rings during this time. One thing it did was measure gravity. There were also instruments on board Cassini that could measure bits of gas and bits of particles in the space between the planet and the rings. We wanted to do this. We expected there to be some, because you knock material off the rings all the time. Some of it evaporates. Some of it gets transported by magnetic fields and all sorts of complicated things and flows into the planet. The idea was, cool, we can measure the composition of the rings and see what this non-water stuff is. And those instruments were successful. They measured this. What was surprising was how much stuff they measured. One of the instruments in particular, one measuring gas, very simple molecules, measured a ridiculous amount of material flowing from the rings into the planet. Specifically, 10,000 kilograms of material is being lost from the rings into the planet every second. Now, if that's right, and that's the average mass loss of the rings are going to lose a significant fraction of their mass in about 100 million years. Now, that people saying that made people go, okay, the rings must be young. There's still ways around it. One of the weird things about this result is that gas flowing from the rings to the planet, it has some amount of water in it, but it's mostly carbon. The rings aren't mostly carbon, but carbon is preferentially flowing into the planet. We don't know why, but it could be keeping the rings clean, in which case the previous argument doesn't work anymore. This is where we are now. People are trying to see if they could self-consistently figure out this and the previous measurement. But trying to make the rings old with this much material flowing between them and their current mass is really hard. People who are arguing for the old rings, there's still legitimate arguments there. We still need to check. But that's got to be kind of, I would say they're in a defensive position right now. They're trying to make it's like, could it still work? Maybe. But right now the data is kind of pushing us to seriously consider the possibility that the rings are only a couple 100 million years old. And how does that work? How can that happen? We now need to go back. We need to have something happen recently to make the rings. We need to get something close to Saturn. Well, what is that something? There's two options. It's something from outside the Saturn system or something from within the Saturn system. It's either a big comet or one of Saturn's moons. In practice, it can't be a comet. First of all, it would be a really big comet. For comparison, the mass we need in the rings is 100 times the mass of the thing that hit us in 65 million years ago that killed off all the giant dinosaurs. The rings is 100 times more massive than that. There aren't many objects that massive. But there's a better problem. Bigger problem. Bigger is a better problem sometimes. Anyway, the whole thing is people have looked into the possibility that a comet gets close enough to Saturn to create rings. The way they do that is they create a numerical simulation. They take a bunch of planets, set them up in a computer, and pitch comets at them and see where they wind up. When they do that, they reliably find that Saturn, out of all the giant planets, gets the least amount of material. Turns out, and it turns out for very simple reasons. Jupiter is more massive than Saturn, so it collects more stuff. Uranus and Neptune are less massive than Saturn, but they're further from the sun, so they have a bigger gravitational sphere of influence. So the problem, though, that means if you put a comet and made Saturn's rings from a comet, all of the giant planets should have rings like Saturn, because it's easier to do it at the other planets, and they don't. This is why most of us think that it's got to be a moon. One of Saturn's moons may have strayed close enough to the planet to break up. It could have simply migrated, or it could have gotten hit by something, a more normal-sized comet that was enough to break it into pieces and produce a disk that went around it. And people are seriously considering this now. Now, just to say, this is a debate those of us working on rings were emotionally prepared for. The idea that the rings could be young was something that had been building over decades. And we aren't comfortable with it yet, but we were prepared for it. At the same time that we were beginning to find this data that the rings were young, other observations were forcing people to call into question the age of Saturn's moons, which makes this story a bit more complicated. Saturn has a lot of moons, and there are lots of different moons, and they're all special. This shows just a diagram showing where the moons are and some of them to scale. The largest of Saturn's moon is Titan. This is an awesome moon. It has an atmosphere of nitrogen, and it has lakes of liquid hydrocarbons on its surface. It's really cool. It is not part of this story. The ones we're interested in are Mimas, Enceladus, Tethys, Dione, and Rhea. They're mid-sized moons orbiting between Titan and the rings. One of those moons, Enceladus, is geologically active and therefore very interesting in its own right. The other four, like Mimas and Tethys, are covered with craters. That's basically all you see, a bunch of craters. Mimas is the one that got famously compared to the Death Star, which is a crater. Tethys also looks like that, but didn't have as good a picture, so meh. But these things are covered with craters, like Earth's moon. The standard assumption that pretty much everyone made is that these objects are old. They've just been sitting out in the outer solar system, getting pummeled by comets and asteroids for 4.5 billion years. And everyone was happy. Then a couple of years ago, some people found some data that was inconsistent with that. Not by looking at what they looked like, but by looking at how they moved. There was a team of scientists in the UK and France who were trying to figure out the orbits of these guys, match all the observations to an orbit. And I mean all the observations. These guys were in France and UK. They had hundreds of years worth of data. And they wanted to fit it all, figure out how fast these things were going around. And the reason is these moons interact. And if you can measure that interaction, you can learn something about their interiors. What they found was, though, to fit all that data, the moons can't be going around the planet at a steady rate. They're slowly spiraling out. All of these moons are spiraling away from Saturn at a speed between 1 and 10 centimeters every year. Now, they're hundreds of thousands of kilometers away from Saturn, so this isn't a big thing. But it's detectable. And we understand what it is. Earth's moon is moving away from Earth. And that process happens because of tides. If you have a moon orbiting a planet, it raises tides, just like it does in Earth's oceans. Since the force of gravity is a little stronger on this side of the moon, of the planet than this one, it creates a bulge. But the planet's rotating, so that bulge gets pulled out of alignment, which creates an asymmetry in the gravity field that pulls the moon ahead in its orbit and causes it to migrate out. This is what's happening on Earth with Earth's moon. We can measure this very well because, there were astronauts up there that put nice shiny mirrors up there. And it's happening here at Saturn. The idea that it's happening at Saturn was not ridiculously unexpected. The rate is really surprising. That's how fast the moon is moving away from us. That's happening because Earth has oceans and land. The oceans form a nice tidal bulge, and then the continents run into them and push that bulge really far out of alignment. Saturn is a gas giant made almost entirely of hydrogen and helium. It wasn't supposed to be able to do this. Jupiter doesn't do this. We don't know why Saturn does this. Yes, I don't know is an answer that lots of us use. But it has implications for the moons, because these moons are migrating away from Saturn. So in the past, say 100 years, they were maybe a couple of meters closer to Saturn. Closer to Saturn means their mutual gravitational interaction is stronger. So they were migrating faster 100 years ago. Go back 1,000 years, they're maybe a kilometer closer to Saturn. They're moving even faster. You start trying to extrapolate this back in time, and things go interesting very, very quickly. This is just, again, a plot showing how far the moons are from the planet as a function of time. You start from today, and then just given how fast they're migrating outwards, and making some assumptions about how Saturn's interior works, you just start extrapolating back. And what you end up with is a bunch of moons inside the planet within the last billion years, which doesn't make sense. So this is a problem. Now, this does assume something about the planet's interior, how it reacts to moons. You can make different assumptions about that, and people did. They made very different predictions. This is a different model. And the moons don't migrate nearly as far. They could be 4 billion years old with this other model, which was actually developed to explain why the moons were migrating so fast. Now, you might say this isn't predicting anything, but the people who made these new models were kind of happy because it meant the moons could still be 4 billion years old and you don't have any contradiction. So everything is fine. It's fine. It's all fine. It's not fine. One of those moons still has a problem. Rhea. Rhea has a problem. You might wonder why Rhea has a problem. It's because Rhea's orbit in particular is very close to something called the evection resonance. It's an interaction with the sun that would distort its orbit. So, turns out Rhea doesn't seem to have gotten close to that resonance, which puts a pretty stringent limit on how far it can go. Just to unpack that a little bit, what do I mean by evection resonance? This gets a little technical, but I'll try and explain it as best I can. Imagine you have a moon around a planet orbiting the sun. Put the moon on not a circular orbit, but an eccentric orbit, one that gets alternately closer and further from the center, from the planet. That orbit has an orientation, a long axis. And that long axis drifts around the planet at a particular rate that depends on how big it is. You make it bigger, it drifts more slowly. When you're in the evection resonance, the rate at which the alignment of the orbit changes is the same as the rate the planet moves around the sun. So as we go from up here to down here, and this thing, touchpad, is kind of sensitive. The moon's orbit changes by 90 degrees, but the planet moved a quarter of the way around its orbit. So the orientation of that moon's orbit is always 90 degrees to the direction to the sun. That allows the perturbations from the sun on the moon to build up. Every time that moon is closest to the planet, it's heading towards the sun. That means it gets a little extra pull, which means it can make that orbit more and more distorted over time. It also turns out it can tilt it. If Rhea ever got into this configuration, its orbit should be tilted and distorted. And it's not. The tilt produced by this effect is an order of magnitude more than its observed value. And maybe you can get rid of that. Nobody's figured out how. But it suggests that Rhea never went through this particular configuration during its migration. The problem is, in order for it to get into that configuration, Rhea's orbit has to cross that red line. And regardless of which model of Saturn's interior you use, it will have crossed that red line a few 100 million years ago. Nobody's figured out a way around this yet. Maybe somebody clever can, but it really looks like Rhea has not been migrating outwards for more than a few 100 million years. This is disturbing. And together with the evidence that the rings might be a few 100 million years old, we start to have to wonder, did something happen to Saturn a few 100 million years ago that not only made the rings, but did something to all of the moons inside of Titan? If that's true, we're talking about, honestly, a catastrophe, because we're now not just talking about something affecting the rings, which are down here. We're talking about something that affected this entire region. And if it affected the moons have 100 times more mass than the rings. We're now talking about a much more extreme event. And lots of us aren't comfortable with this. We were already having trouble thinking about a moon breaking up around Saturn just by a single impact. We're now talking about something much larger. And I will say, a lot of people are trying to see, do we really have to consider this? But we at least have to think about it. So, to wrap up, I want to tell you a story. This isn't a theory. This isn't even a hypothesis. We don't have enough background information to make this either of those yet. This is just a bedtime story for what might have happened. And I want to make that clear. It's not a theory. When Saturn formed, it had two large moons, one orbiting at a fair distance. This is Titan. It had a second large moon, orbiting interior to it, a fair distance away. Perfectly fine. It formed like this, and it's been like this for billions of years. And this thing has been relatively sedate. And the only thing that's happening is the tidal interactions are causing the moons to migrate away from the planet. The outer moon, Titan, is just doing that. It's fine. The inner moon happened to form inside the evection resonance. So for a long time, it just migrates out and isn't anybody's problem. But at a specific time, it gets into a resonance, something that perturbs its orbit. The evection resonance is very strong if you let it get going. It can significantly distort an orbit. It can cause something to start following a very eccentric orbit. This could start to be a problem. If you make this orbit distorted enough, you can cause this moon to get close to Saturn's Roche limit, where it will break up. If you make the orbit long enough, it can crash into Titan and be broken up. Even if you just distort it a little bit and there's a third moon in there somewhere, they can run into each other and break up. But the thing is, that material from that event, that disruption, is thrown all over the place because that original object was on a very distorted orbit. The debris from that collision, however it happened, then begins to collide with itself at fairly high speed, forming a debris disk. The outer parts of that debris disk are outside the orbit of Rhea. They're outside the Roche limit. They begin to coagulate under their own gravity, forming a new set of moons. The inner part is inside the Roche limit and settles down to form the rings. Now, is this what happened? I don't have a clue. The only thing I'm saying is it requires one weird thing to happen. A moon needs to get into a very peculiar orbit for this to work. But it just needs that. Is it what happened? No idea. And if any of you guys have a better idea, I would love to hear it. Thank you all. And I'm supposed to take questions now. So, okay.
Okay, given that speculation, the debris wouldn't be ice then. That's the question I have, is how can you correlate those two things?
So, you're right. The debris would not be pure ice. And in fact, the moons are not pure ice. There is, so, an interesting thing about ice versus rock. Rock is much easier to hold itself together. When you go inside the Roche limit depends on what your stuff is. The Roche limit for ice exists outside the region for the Roche limit for rock. So if the material is starting to come apart, a rock going through there doesn't get broken up, but the ice does. So the ice can be preferentially delivered to the part near the rings. This is definitely one of the things we would have to figure out to make this a proper theory. We're still not there yet, but that is actually one of the issues.
This is a question. I'm gonna turn the lights on, folks, so just to give you a heads up.
Okay, go. Okay, that one.
What is Rhea made of?
So Rhea is made out of a combination of, I'm trying to remember the exact ratio, but it is made out of both ice and rock, which we know from measuring its density. All of these moons have some fraction of ice and rock, whereas the rings are pure ice, and that is an issue. I'm just going around this way, so go ahead.
About the first question. So if it's within the Roche limit, how are there moons inside of the rings? Does that mean because of the rocks together, or?
Okay, so just to repeat that. So going back to that first image, basically, which is fine. It's, so There, see? So this thing, how does that work? So the Roche limit is a little bit fuzzy. We're technically inside the Roche limit for Earth, but we're not falling apart because we're not held together by gravity. We're held together by chemistry. Chemical bonds are a lot stronger than gravity. That thing is probably a solid chunk of ice. Now, why did so if you can smash enough material together to make it solid, you can stay together inside the Roche limit as long as nothing hits you. If that thing gets hit by a comet, it's not coming back together again. Okay. Going over to this. Sorry.
Yeah, I have a question. My question would be, you showed that it has so many moons, and then some of them were like really rinky-dinky things that weren't round and stuff like that. So my question would be, are those, the chemical makeup of those, whatever they are, that are orbiting the moons or whatever, are their composition not 100% ice, or exactly like the other moons and their amounts of the different compositions that maybe the one of them hit and shook off the ice, and now it's not all the way with the same amount?
No. Okay. So the reason some of the smaller moons aren't perfectly round isn't mostly due to their composition. It's just due to their size. If you're big enough, your gravity is strong enough to crush you into a sphere. If you're a little bit too small, it's like it all wants to hold together, but it's not enough to push ice into a round shape. And it turns out that where that transition happens is almost exactly the mass of the rings. I've never thought about that before. I don't know if that's relevant, but it's interesting. Okay. Yeah. Okay, let's go.
Are there any of Saturn's moons that would have a chance of getting a life scenario?
There is one. There's actually multiple moons that could potentially have life. There is one that is very, 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 very likely to have life. This is Enceladus. Enceladus is that moon I mentioned is geologically active. I'll just get to it again. There it is. So, Enceladus is not covered with craters. It's covered with fractures. Those fractures in the South Pole are vents. They're geysers. Coming out from the bottom of Enceladus are fissures that are warm, like close to the freezing point of water. Underneath, it's almost certainly liquid water. What's coming out is water vapor, ice crystals, and organic molecules. So there is organic molecules, water, and energy. If there is life anywhere, that moon is the place to look for it. And lots of moons might have liquid water under their surfaces. This one's venting it out. This is a heavy target. This is one of the other moons. We want to go back there and measure this. The spacecraft, we didn't expect this. All the instruments I conceived did as much as they could to measure this. We want to go there with machines designed to look for if there are living things connected to that. But yes. Yep.
Would you clarify what you mean by organic molecule?
Oh, sorry. Organic molecule means molecules containing carbon, which is a big component of life. The problem is the instruments on board couldn't be any more specific than that. There are molecules that contain carbon in the plume, which is a good thing if you're looking for life, but not dispositive at this point, unfortunately. Yep.
What's NASA's follow-up to Cassini?
Well, there is one currently ongoing that has just been selected. So just to say, the way it works is there's never something that's strictly speaking a follow-up to another mission. Each thing tells us something and then we go do other things. The next mission to the Saturn system is something being, with heavy involvement from somebody else at the University of Idaho, is another mission to Titan, which is this giant moon with an atmosphere and lots of complex chemistry on its surface. There is now a mission being built. It will get there, being built, and will be launched and finally get there in the 2030s, because getting out to the outer solar system takes a while. It is going to be, and I will say it this way, a nuclear-powered quad drone that will fly around Titan's, which is basically going to land on the surface and measure its chemistry. This is something that's looking in great detail at Titan, which is a really cool boon on its own right, and something easy to get to because it's got a thick atmosphere. People are now talking about whether we should have a mission to Enceladus, and can we get something that's going to sample that plume and tell us the answers that we want. That's a harder technical problem, and we're still working on how to do that. Other ones of us would love to get a mission to the rings. That's a bit more niche, so we have to figure out if we can do that affordably. Yep.
Before we take any more questions, I just want to let you know it's 8:30 now, so let's go ahead and give Professor Hedman a round of applause. If you're interested in visiting our observatory tonight, head out to the lobby. The students will take you up there, and I'm sure Professor Hedman will be happy to continue taking questions.
Yep.
Thanks for coming.
Okay. Oh, here's one.
You said that there were, you can see the splotches and you can imagine foreign objects.
Yep.
Are the objects in Saturn
I can answer that once things. What? When? Oh, God. 2002. It's all up in Moscow. Mostly physics. So, like intro physics and, not much astronomy. Just resources. A couple meters. The rings are the flattest object in the world. Yeah, no. If you want to make a scale model of the rings out of paper, you need a sheet of paper. Yeah. Yep. They are ridiculous. It would be cool. The trick is it's moving at 30 kilometers a second around Saturn. So making a spook that works like that is hard. And to get to your question about things, so yeah, the ring particles are constantly crashing into each other, but they're doing so because they're all moving around Saturn at about the same speed. They're literally crashing into each other like this.
Right.
So that doesn't create a cloud of debris. It just crunches the surfaces. Sure. So yeah, that is what happens when something hits it at high speed.
Okay, so it's actually due to actual interactions, not just due to the way it goes.
No. Yeah, we think that's actually smacking two things together and breaking.
Gotcha. Yeah, because I always imagine objects in space are much farther apart. So I'm like, the actual idea that something's crashing into the rings.
If you were on the particle, you'd see the other hand.
Oh yes.
It would be that obvious.
It would be that obvious. That picture I was showing you was not exaggerated. That's what it would be like to stand on the rings.
So what would it just kind of be in there? You get close to the solar system.
Well, that's the thing. It doesn't need to have. So the thing is, the gravity of the rings is so low. It needs to be something that kind of grabs. It wouldn't need to have any ability to move. Like a little bit of thrust is enough to leap from one particle to the other. What you need is a way to hold on. This is actually like on Enceladus. You think, oh, we need a rover to drive around. You don't need a rover. All you need is a little rocket, and with a little bit of thrust, the gravity is so weak, you'll just hop a fair distance. Mobility on these objects, it's keeping it under control. That's the problem. Like when people tried to land on that comet, it didn't anchor right, and so it bounced. And it bounced a fair distance. Yeah, that's the same problem. It's like, in this case, you need to land somewhere that isn't going to get crushed by another green. So that's the challenge. So the challenge is getting into the rings because they're moving so
Are
fast.
all of the rings uniformly isotopic way, or some of the rings different compositions?
Some of the rings are more rock rich than others, but there are compositional variations across the rings, which tell us something about the history of the rings. But they're all still pretty ice rich. Like there's a little bit higher rock in the part closest to the planet, and whether that's telling us something is another question altogether. Yeah.
It's really curious to have a huge amount of new material going in more than we expected.
No, that was surprising to everyone. It was like, that can't be right. But nobody's been able to figure out what the calculation did wrong. So, yeah, that we don't know how that's even happening at this point in time.
So the likelihood of a mission to the rings or to the Celestium is probably, 100 years out or something?
Hopefully not that long.
Yeah.
But it would probably be 10 to 20 years before we could even get there.
Yeah.
So, yeah, I mean, we're talking about missions like that, but it would take 20 years before they could be developed. So, yeah, the next mission to the Saturn system will be Titan. It will get there in the 2030s.
So what kind of observations can it make about Enceladus while it's there in Titan?
No.
None at all.
None at all.
Consider it a
Not at all.
Wow.
It literally can't the way it's operating, which it's a landed thing on the surface of Titan, which has thick, hazy atmosphere, and it's on the side that isn't facing Enceladus. So, no. People have thought about it. No. Whether it could carry something is another question, but that's another. But yeah, unfortunately, and the instruments are different that you'd want for the tube. So it's not. It's like maybe we could do a couple things on the way in, but it's not going to answer the big questions for us. So that's it.
So which side do you lean toward?
On the young rings, I'm going. The case for the young rings is very strong. I'm a person who follows this orbit dynamics quite a bit, and I don't see ways to keep the system old and have all of the properties it has. I'm willing to be convinced the rings are old, but right now it seems more natural to think that they're young, which is part of the reason it's fun to speculate about chaotic things happening in the last few 100 million years. I mean, if somebody came up and told me tomorrow, it's like, we just did a detailed evolution model of the rings and found that it's totally fine for the rings to be 4 billion years old. It's just because this quantity balances that quantity. I'd go, okay. But then we'd have to look at that carefully and see if there are any implications for that.
Speculation on what's causing all that carbon to go towards Saturn?
I wish we knew.
What was the question?
What's causing the carbon to preferentially go towards Saturn?
Yeah.
We don't know, and nobody has yet fully explained that. There are some people who think it's because the instrument wasn't. Water is a really nasty molecule. It tends to stick to things. So people have considered the possibility that water may have just not been measured in the appropriate way. The people who study this have done a lot of things and said, no, that can't be the whole explanation. But yeah, it's not clear because unbalancing things to the extent it seems to be unbalanced is weird. One possibility is maybe we're not seeing typical ring flow, we're seeing something that, like a specific event, like maybe some comet recently broke up and we're seeing the organic molecules from the carbon from that comet drift in towards the planet.
Is the composition of the inner moon such that if you had to develop a story into a theory, that they could always seem as something? Is there something about them that makes them like is it there?
Not clearly. Their densities are all over the place. The one thing about them that seems systematic in a slightly curious way is their mass. The further out you go, the higher their masses are. Their densities are all over the place. Enceladus is more dense than Dept.
Different materials.
They're different materials, but the amount of stuff seems to follow a fairly regular trend. And people had used that to say that some of these moons early on had spawned from the rings. You had this huge massive ring that spread out, clumped together, formed moons that then migrated away. And the problem was, to make that work, the rings had to be 4 billion years old. And so, and again, Rhea still has its problem. But this whole thing, yeah, so there are trends that seem to suggest a common origin, but not necessarily that they all came from one thing. Let's phrase it that way.
I have a question. Given that the objects we know of are not so pure in water as the rings, given all the theories that you kind of brought up have the shared issue that we don't know why it's being purified?
So, not entirely. Because of differences in the scale of the Roche limit, you can have something where a moon gets torn apart and preferentially the icy material ends up deposited as a ring and the rest of it either falls into the rocky part falls into the planet or escapes. So you can create a system, you can create, in principle, an ice-rich ring to start with. And then, if it's only a couple 100 million years old, it hasn't been polluted. Because of the different mechanical properties of ice and rock, you could potentially make a ring that's very ice-rich. It is still a bit of an issue whether that you can do it to the level that is needed. But whether that makes the problem better or worse is kind of up to you.
So, what do we know about anything about the composition of rings around other planets?
So, the rings around other planets most of it is very fine dust, just kicked off of moons. The only other planets that have dense rings the only other big one is Uranus. Its rings are dark. They're made primarily of carbon compound. They're probably made somewhat of ice, somewhat of carbon compound. They're about as bright as comets. The other object, there are now tiny little objects called centaurs, which are basically gigantic comets running around the outer solar system. 2 of them have rings.
Oh, wow, really?
We don't know what they're made of. There's also an object out beyond the orbit of Pluto called Haumea, which has rings. We now know small bodies have had rings. We've known about this for maybe 5 years now. We don't know why they have rings. Because asteroids don't have rings. We have never found an asteroid with rings, but objects in the outer solar system have rings.
So with all the infall, I'm sorry, I'm kind of fascinated by the infall, the carbon and the ice. All this is coming in. What's putting it back out there?
Nothing.
Really? So someday they'll all be gone.
Yeah, this would say that the rings are eroding.
Yeah.
That the rings are losing mass.
Yeah.
There is nothing that. Now the thing is, that's something that kind of works in a kind of exponential way. If you lose like half your mass, you get half the rate of material. So it kind of takes longer and longer as the rings get less and less material. So, if it takes 100 million years for the rings to lose all of their mass at their current rate, that's probably not the right extrapolation. They'll probably lose a significant fraction of their mass, but it might take much longer for them to completely erode away. So, yeah. Are there other questions? Yeah.
So just completely random question, just as showing images here.
Yeah.
Has anybody thought about the idea that maybe this is all coming from Saturn and it's just being populated by the atmosphere of Saturn?
You mean all of these moons and things?
Well, so let's say that slowly you've got hydrogen and oxygen coming off the surface, and that's creating the rings, and then the rings are colliding with each other and they're creating larger objects, and those larger objects are expanding outward.
So, not really. The problem is that would require so the basic problem with that is that getting something further from the planet and into orbit in particular. Things orbiting the planet relative to the planet itself are moving at tens of kilometers per second.
Mm-hmm.
So you need to give them a lot of energy and angular momentum to get out there. And nobody can think of how to take material that was close to the planet, that was mixed in the planet, and somehow give all of that to a small chunk that then moves off.
What if it wasn't a chunk, but it was gas?
Well, I'm still saying it would have to be a subset of the gas that makes the entire planet. Usually things mix so that energy and angular momentum get kind of uniformly distributed. What you're asking for is for one chunk of the planet in the form of gas or particles to suddenly inherit most of the planet's a good chunk of the planet's angular momentum. And we don't know how to make that happen. Let's phrase it that way. Also, the planet, for better or for worse, is mostly hydrogen. There is, at the surface levels that we can see, there's very little oxygen. And you need that for water.
The oxygen is part of the equation.
Yeah, so the water in Saturn's atmosphere is deep. We don't know how deep because it's deep enough you would have to send a probe in, and we've never dumped a probe into Saturn.
But there is water.
Yes, there should be water in Saturn. We are pretty sure there's water in Saturn. How much water has not been measured accurately yet. You need methods like seismology and gravity field analysis to figure that out. But even then, it's is it rock, or is it water, or is it carbon, or is it that? And it's been very hard to measure those quantities because they're so deep in the atmosphere. Yeah. Any other ones?
Has there been thought and put into the effects that just the sunlight itself has on the rings in terms of doing anything to elevate its orbit or
sunlight?
De-elevate the orbit of the carbon more rapidly with black or something like that?
That's interesting. I don't think anyone has done that specifically. That is the sort of thing that we now have to seriously start, or not me, because I'm not a UV chemist, but somebody needs to start thinking about those sorts of things. It's not out of the question that something different about the ion chemistry of carbon is so different from water that it makes it really efficient to transport. But nobody's figured it out yet. Yeah.
What would be the reason we want to go to Titan as opposed to Enceladus, given that it has a higher probability of having organic life?
So the main reason to want to go to Titan, so it's a slightly different question. On Titan, so to have life, you need three things, right? You need water, or a solvent, you need energy, and you need complex organic carbon-bearing molecules. Enceladus has all three, but the complex organics, or the carbon molecules, are actually a fairly small part of the plume. So they're really hard to measure properly. Titan's surface is covered in dunes made out of basically sludge. The atmosphere is mostly nitrogen, but nitrogen is our atmosphere, it's transparent. That orange color is methane, ethane, acetylene, propane, every complex organic molecule, and it's covering the surface. And the thing is, because it's got an atmosphere, it's easy to land on because you can brake. So if you can land on Titan, we have the one place we can study how organic chemistry, how chemistry of complex organic molecules works, and how far it can go without life. And that's a big deal. And in principle, there's places where impacts happened where water might have gotten involved. So it's the reason to go to Titan is it is an interesting thing from the point of view of understanding these sorts of things. And at the moment, the technical availability of doing this is here, whereas on Enceladus, it still might be a couple years away.
Got it. Thank you.
Yep.
Do you know what the diameter of Titan is?
It's about this. It's a bit bigger than Earth's moon.
Got it.
So it's about the size of Ganymede. It's a fairly big object. It's about the size of
Do we have the biggest moon relative to all the other planets relative to the size of Earth?
Depends on how you define a planet.
Okay.
If you take the standard definition that the planets are Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, then yes. If you are of the persuasion that Pluto is a planet, Pluto Charon is closer to even mass than Earth is. They're so similar in mass. It isn't so much that Charon is orbiting Pluto, they're actually orbiting their common center of mass, which is outside of them. So it depends on how you choose to define a planet, which is as far as I'm going to go on that subject. Cool. Any others?
Oh, thank you. I was going to ask, we've been talking earlier about Enceladus and how it's those plumes of essentially salt water and organic matter are going into the D ring.
The E ring.
Sorry, the E ring. The E ring. Do we have the ability, currently either Earth-based or in orbit, to do some kind of spectroscopic analysis of that, effectively that ice, that compound ice in the E ring, to get an idea of what's in it?
So, yes, but not spectroscopically. We have spectra of the rings, so we can measure of the E ring. We can measure their composition. So we can look at how much light they reflect. The E ring is this very tenuous thing centered on Enceladus. Enceladus is geologically active. There's this plume of material escaping. That entire ring is what's coming out of Enceladus. When we look at it in remote sensing, like look at pictures of it and look at it at different wavelengths, we can see its ice. So it's primarily ice. The problem is other things like salt or carbon compounds are a small fraction of the ice and don't have strong spectral signatures. They don't have clear absorption bands in the near infrared. Organics can, but at wavelengths where it's really hard to measure. So the way we know the composition of those particles as well as we do is we had a spacecraft fly through them with instruments that were designed to measure the composition of gas and little particles that run into them. Those instruments, basically something comes in, it hits, it breaks up into its molecules, those molecules are separated out. It's called mass spectroscopy. And that instrument flying through that was what told us that in addition to being ice, some of them had salt, some of them had complex organic compounds, some of them have rocks. But we can't see it from remote sensing. We can only get that level of detail from an instrument flying through it. Now, in the future, with very good spectra, could you do better? Probably, but they're small. It makes it tricky. Yep.
Want a break or you good?
Fine. But, you guys need breaks?
He's had a long day, I just want to make sure he's worn out. He's got an early flight tomorrow, too.
Yeah, that's fine. But anyway.
Thank you.
There you go. Oh, happy to help. Yep, you guys. I'm fine. I like people asking questions. Oh, answering questions is fun. Or questions where I'm happy to say, I don't know.
Wouldn't it be wonderful to somehow migrate all this extra water out of the outer reaches into Mars?
Maybe. I like this stuff more than Mars. But yeah. Well, Mars has plenty of water. It's just all frozen. And so is all this.
I thank you. Really enjoyed your presentation.
Oh, thank you for saying so.
Questions.
Yeah. No, I'm happy to do so, and thank you for being interested.
Where do you teach?
University of Idaho. So up in Moscow. Yeah.
And sorry, I was messing with you a little bit. I'm always curious to see how people answer certain questions.
Okay.
Actually, one of my buddies is working on, he works out at JPL, and came up with the Titan submarine.
Oh, yes. Yeah.
So,
A Titan submarine would be awesome.
yeah.
That's even harder to do.
Yeah. I didn't say that it was. He's already working in Amazon, but when he was at JPL, he came up with that. He got an award for it, and that's the last thing I heard.
Yeah, people have talked about it. It's just, but the previous proposed mission to Titan before the quadcopter was actually a lake lander.
Yeah.
Which would have been cool, but didn't get selected.
But I mean, I don't want to be a downer for like the reality is that any place that they think there's life until they can get this stuff clean enough, they're not going to send anything.
That is another concern.
Yeah.
And the nice thing about Enceladus is, it goes out of where it's it's not habitable on the surface.
Yeah.
So you can go there and go, okay, we're collecting all the dead bugs.
I think they're swinging in the direction of the rings now.
Oh yeah, well that's definitely the next step.
Yeah. Thank you.
Thank you.
What's your favorite science fiction movie?
Oh boy.
Don't say the Brad Pitt one.
But which one's that one?
It's that new sucky one that came out.
Oh no, Ad Astra. I haven't even watched it yet.
It's the most depressing thing you did.
I honestly don't know. Yeah.
Do you like Interstellar?
Interstellar's the most optimistic.
Yeah, there were things about Interstellar I liked. I don't think I liked it overall as a movie just because it's kind of like watching, like, say, Avatar and going, why are we watching all these people do crap? I just want to watch the animals run around. And I have a similar feeling, like, for Interstellar, it's like, oh, there's all this cool stuff about black holes and things like that, and there's these people talking, and I don't want to. So I almost would go, like, I almost want to say Koyaanisqatsi, but that's
Which one?
One of those movies that just shows, like, animations of things going off in space. So but yeah, I always have a hard time on that. Yeah.
Did you like The Expanse?
I got into that one, yeah.
Yeah.
No, I've only watched the first season so far because time.
Further into it. They got a budget finally.
Yeah.
Took it up a notch.
Kind of was nice when they were like kind of constrained to be. Yeah. So yeah, I've only watched the first season. I'm kind of like, oh, this is cool. So.
It's probably the most accurate.
Yeah, I mean, there's definitely that.
Yeah, it's dead on accurate.
At least until they start doing. I mean, I've seen enough of the previews for the previous season going, I think they're beginning to stretch things a little bit at this point.
Well, yeah, they got to introduce aliens and that kind of stuff.
Yeah.
But, at least when it comes to the tech and the stuff going on around Mars and everything.
Yeah, it was kind of...
The G-forces, you have to pay for those. And
the difference in the people that grew up in the belt and on Mars and how gravity affects them.
Yep. No, that sort of stuff I started going, oh, this is cool. And it was cool enough that I went, oh, and they're talking. Okay, I'll pay attention now.
You know what's interesting about The Expanse? It's very political, but it's apolitical. I mean, it doesn't take a position of anything. It just presents a lot of, people working to gain power and things, but it doesn't take a position. I don't sense any bias in The Expanse at all.
it's like South Park.
Yeah.
It's made fun
The
of.
South Park, right.
Yeah.
Thank you, Mike.
Thank you. Thank you for coming by. Yep.
Oh, crap.